morning, everyone, both here and online. It's great to actually be doing events in person again for those who are here. It's a wonderful opportunity. So today I'm going to talk to you, kind of setting the stage really for the subsequent discussions about the noisy measurements. In order to understand the noisy measurements file that may be created, it's helpful to understand kind of the basics of how the 2020 Census Disclosure Avoidance System actually works. Now, it is important to know that the disclosure avoidance system is actually a collection of different algorithms that are being used all within the framework of formal privacy to protect the various data products that comprise the 2020 census. The first of these algorithms is the top-down algorithm, which we'll be focusing on today. In discussion or in subsequent conversations, we can talk about some of the other algorithms that are being used for subsequent data products. Now, the top-down algorithm is the one that was used to produce the redistricting data that was released last August, and it's also being used to produce the demographic and housing characteristics file that's coming out in 2023. Now, before I start, I do want to thank all of my many colleagues at the Census Bureau and amongst our numerous partners for all of the work they have done and for their contributions to the information that's included here. I also want to thank all of our many stakeholders and external data users who have contributed invaluable information that have helped us in this endeavor all throughout. Lastly, any opinions and viewpoints I express today are entirely my own. Okay, so the 2020 Census Disclosure Avoidance System's top-down algorithm implements formal privacy protections for the Public Law 94-171 redistricting data summary file, which I mentioned, released last August. It's also planned for use in the demographic profiles, the demographic and housing characteristics file, and the special tabulations of the 2020 census. Now, when the Census Bureau's Data Stewardship Executive Policy Committee essentially made the decision to move towards formal privacy for the 2020 census, they did impose a number of system requirements that the disclosure avoidance system in general and the top-down algorithm in particular had to meet. The first of these was the top-down algorithm had to exist within a predetermined data processing environment. So we had to ingest data in a pre-specified format in the form of the census edited file, which is the confidential microdata of the 2020 census. And we had to be able to output privacy protected microdata to feed into the decennial census's tabulation systems. So we did have this microdata input and output requirement. The DSIP also said that we needed to ensure that certain variables were held invariant, meaning that there were certain tabulations to which no noise would be added. For the redistricting data, that included state population totals and the number and major type of group quarters facilities at the block level and the number of housing units at the block level. Additionally, the top-down algorithm needed to be able to impose the various edit constraints that are used for the census edited file, as well as impose structural zeros. So for example, you can't have a 13-year-old grandmother. So those had to be built in. Perhaps most importantly, the system needed to be able to tune the accuracy or utility and privacy trade-off for pre-specified tabulations. So we needed to be able to kind of fine-tune how the privacy loss budget was going to be allocated to ensure fitness for use and privacy protection. The system needed to be asymptotically consistent, meaning that as you increase the privacy loss budget, you should get more and more accurate data. Eventually, if you increase it all the way to infinity, it should spit out the confidential census edited file as the microdata output. And kind of germane to our ability to have these discussions today, unlike many of our prior disclosure avoidance techniques that we and other agencies have used, there was a major system requirement that everything we do be able to be fully transparent, that we can share our code, we can share our parameters, and we can share our analyses of the relative accuracy and relative privacy. So at a very high level, the top-down algorithm works along this kind of process flow. It ingests the confidential census edited file and the geographic reference file. It converts those microdata into a corresponding histogram. It takes a series of noisy measurements, and we'll be talking more about that today. It then post-processes those noisy measurements, and then it converts the resulting privacy-protected histogram back into microdata. So for those who may not be familiar, I know I wasn't when I started on this project, what is a histogram in the context of the disclosure avoidance system? I'm a statistician, I'm familiar with the way statisticians typically think of histograms, and this is slightly different. A histogram is essentially a tabular equivalent to microdata. So essentially in microdata, you have one record per respondent, one record per unit of observation. In a histogram, you have a record count for each unique combination of attributes, including location. So you can see an example here of kind of block level race and sex data being converted to the corresponding histogram for those microdata records. The important thing here is that they are functionally equivalent. You can convert microdata to histograms, and you can convert histograms back to microdata. Noisy measurements. So the top-down algorithm allocates shares of the overall privacy loss budget by geographic level and by query. And then each query of those confidential data have noise added to the answer to that query. The noise is taken from a probability distribution, the mean of 0, and variance that's determined by the amount of privacy loss budget allocated to that query at that particular geographic level. Each of these noisy measurements are independent of each other. They can include negative values, hence the need for post-processing, which I mentioned a moment ago and which we'll talk more about. Now, to give you an idea of like how many noisy measurements are we talking about here? In the context of just the redistricting data, so the Public Law 94-171 redistricting file, the top-down algorithm took over 16.6 billion independent noisy measurements of the CEF. That were then kind of combined and post-processed into the approximately 3.4 billion cells that were included in the resulting published file. So we take a lot more noisy measurements than are actually reflected in the published data. And this will become important in some discussions about what form a noisy measurements file might take. It's important to know that the top-down algorithm uses zero concentrated differential privacy, or ZCDP. It uses a privacy loss parameter rho. This is different from kind of some other differential privacy frameworks that use epsilon or epsilon delta. Now, rho-based PLBs can be converted into epsilon delta equivalents, but they don't convert to any single point of like any single pair of epsilon deltas. They convert to a whole continuum of epsilon delta pairs. So analysis of the privacy protection afforded by our privacy loss parameter rho should use the entire continuum, not just any single epsilon delta point. Now, some formulas do provide tighter bounds on the epsilon delta curve and implied by any particular value of rho. The formula here is the one that we've used for our kind of public conversions that we include in our privacy loss budget allocation tables. Also important to know is that the noise distribution that we use for the noisy measurements is a discrete Gaussian distribution. So the expected variance of any noisy measurement can be estimated by knowing the total privacy loss budget that was expended for the overall file, and the share of the privacy loss budget, the share of rho, that's allocated to that particular noisy measurements query at that particular geographic level. And for the technical details of how to do that, you can see the new technical paper by Aboud et al. 2022 in Appendix B, and I'll have the link included later. So how does the top-down approach work? Well, so we start at the level of the overall United States, so the histogram of the entire US. And we take the noisy measurements for the US as a whole. We take the invariance, which I mentioned before, and we take all of the edits and structural zero constraints that need to be met. And the top-down algorithm then post-processes those noisy measurements into an internally consistent histogram at the US level that meets those various things. So it's as close as possible to the noisy measurements while also meeting the invariance and constraints that have been pre-specified. And the resulting histogram is entirely non-negative integers. which then kind of forms the histogram for the overall United States. Then we move down the geographic hierarchy, and I'll talk more about the geographic hierarchy in a second, but we move from the US level down to the state level, and we take the noisy measurements that were taken for the states, and then we find the histogram at the state level that most closely matches those state level noisy measurements, while also being consistent with the overall histogram that was determined for the US above it. Essentially, you can think about the ball in the hopper here that reflects constraints. At each subsequent level of the algorithm, that constraints ball gets bigger as it incorporates everything that had been determined for the geographic level above it. So then you determine essentially all of the individual state level histograms. Then you move down another level of the geographic hierarchy, et cetera, until you get down to the individual census blocks. Once you've post-processed the individual census blocks, you have a fully formed histogram for the entire United States down to, like, geocoded down to the block level. That can then be converted back into microdata for tabulation. Now, there are a number of benefits of this top-down approach as opposed to, or in contrast to, kind of local DP or bottom-up approaches. The disclosure limitation error of the top-down algorithm does not increase with the number of contained census blocks in the geographic entity. So as you aggregate contiguous blocks together, you do not end up with the error aggregating along with it. Error tends to cancel out as you aggregate those blocks. So the TDA yields increasing relative accuracy as the population being measured increases in general, and increased count accuracy compared to kind of a block-by-block approach. In this way, the top-down algorithm kind of borrows strength, if you will, or borrows accuracy from upper geographic levels to improve count accuracy at lower geographic levels. And this is particularly important in the context of the sparsity that we see in a lot of the cells that comprise the 2020 census, where you have lots of different categories, but very few individuals represented in those categories, and oftentimes zero. So I mentioned the geographic hierarchy. So the Census Bureau's traditional tabulation geographic hierarchy follows a very kind of determined path. It's the US to the state, to the county, to the tract, to the block group, to the block. The top-down algorithm also works along a geographic hierarchy, but ours is slightly different, and we'll be talking more about that, and then my colleague Ryan will be talking even more about this process. Now, the top-down algorithm only takes noisy measurements at geographic entities that are on the top-down algorithm's processing geographic spine. Now, this is important because many of the legal geographies that we're most interested in fall off of the traditional tabulation geographic hierarchy. So in that regard, you're not taking noisy measurements of those off-spine geographies directly, but you can still estimate the relative accuracy of tabulations for those off-spine entities by knowing essentially how far from the spine they are. How many on-spine entities do you need to add or subtract in order to get that geography that falls off the spine? And examples of these off-spine geographies could be anything from school districts to congressional districts, city council districts, etc. Now, because a lot of the uses of census data are really focused on these off-spine geographies, we did want to find ways to improve overall accuracy for off-spine geographies for pre-specified use cases. So to address this challenge, we altered the geographic spine that the top-down algorithm uses to improve these off-spine geographies' accuracy. And this was done primarily, and I apologize for the formatting on the slide here. This was done primarily through the inclusion of a branch in the top-down algorithms hierarchy for American Indian, Alaskan Native tribal areas, and the inclusion of what we call optimized block groups, which are not shown here and which Ryan will be talking about, that helped us kind of bring those off-spine geographies closer to the central processing spine. Now, I do want to make it very clear, the changes to the geographic hierarchy within the top-down algorithm are exclusively for how the algorithm works. They do not impact the published tabulation geographies that everybody knows and uses in the published census data. Also important is to, again, help with accuracy, help with eliminating post-processing bias. The top-down algorithm is able to use what's called multipass postprocessing. I mentioned a moment ago the issue of sparsity. There are a lot of zeros and a lot of very small counts in the cells that we're taking queries of. And those zeros and small counts have the potential to introduce bias when you do the post-processing to create internally consistent non-negative integer counts for all of your queries. So to address the sparsity issue, the top-down algorithm's processing, or I should say post-processing, is performed in a series of passes. So at certain geographic levels, the algorithm constructs histograms for just a subset of the queries in a series of passes for that level. And then it constrains the histogram for each pass at that geographic level to be consistent with the histogram that was produced in the prior pass. So for example, in the redistricting data file, we did this for some geographic levels in 2 passes, where we post-processed for total population counts first, and then went through and post-processed for the remaining tabulations, including in the redistricting file, so that everything in that pass 2 was constrained to the population counts for each geography that was determined in pass 1. Now, in the context of understanding and interpreting the noisy measurements file, it's helpful to understand the privacy loss budget allocation. And again, somehow in moving to this computer, the formatting got screwed up. I will share the actual slides that have the correct formatting. These are the privacy loss budget allocations by geographic level that were used for the production settings run of the 2020 census redistricting data. On the left-hand table, you can see the PLB allocations by geography for the person tables, so P1 through P5. And on the right, you'll see the allocations by geographic level for the housing tables, or the units tables used interchangeably. That would be for table H1. And you can see the fraction, the proportion of the overall global row that was allocated to the US level versus the state level, et cetera. And as I mentioned before, knowing those allocations is a critical component to being able to estimate the amount of variance in the noisy measurements due to DP error. You also need to know, however, how much privacy loss budget was allocated to each individual query at each of those geographic levels. And so this is the breakdown for the persons tables for each of the queries that were asked in creating the noisy measurements at each of the geographic levels. And so you can see the relative proportions of row allocated to each of those queries. I did not include the corresponding table for the units file here because there was just one query included in that. So all of the privacy loss budget at each geographic level was allocated to that query. A full technical paper detailing all of kind of the inner workings of the top-down algorithm, as well as substantial discussions of issues and challenges and kind of interpretation of various factors is available. It is a forthcoming publication, but it's included as a working paper on the Census Bureau's website. It's about it all 2022, and you can get to it through the link included in the slides. And with that, I will turn things to, do we want to do questions after each, or should I turn things to Ryan? Oh, one right. Oh, yeah. I will actually defer to some much more knowledgeable people about that in this audience. So. So the question was, I mentioned in my talk that row-based allocations of privacy loss budget don't correspond to any single epsilon delta equivalent. They correspond to a curve of epsilon delta pairs. and that you kind of convert, you should look at that full curve rather than looking at any single epsilon delta equivalent. The question was, can I talk more about what the implications of that for interpreting the semantic guarantee? And I deferred answering that to some of the much more knowledgeable differential privacy experts in the audience, because I know if I attempted it, I would not do it justice. So.
No?
Here.
Oh, there we go.
There you go. Yeah.
All right. So I'm going to lie a little bit, but intuitively, when an algorithm ensures epsilon delta differential privacy, it's saying that there is a small probability, which is delta, which we set the parameters, so we can make delta as small as we want. But except with this small probability, the outputs that are produced will have privacy loss, which is bounded by epsilon. Privacy loss for a specific output is, you can think of this as follows. Imagine two databases that differ only in the data of one person. And then you look at the ratio of the probabilities of seeing a specific output with the first of those databases versus with the second of those databases. Because differentially private algorithms will randomize, and any given output happens with some probability that is not either 0 or 1 typically, but somewhere in the middle. So you can look for any observation at the ratio of the probabilities of seeing that on these two adjacent databases, and the algorithm should guarantee that that ratio of probabilities is bounded. And in fact, the log of the ratio of those probabilities is the epsilon term. So what this promises is that with high probability, with probability 1 minus delta, the ratio, the log of the ratio of the probabilities for any observation is bounded by epsilon. So as we so some algorithms just have pure epsilon probability. There's a 0 probability that the bound will exceed epsilon or will be less than minus epsilon. But for other algorithms, there's a kind of trade-off, and that happens typically when you add Gaussian noise. That would be one way of having that, and that's essentially what's going on here. If your noise variable is way out on the tails, you're in that bad delta region. If your noise variable is near is near 0, then you're in the good region. And that's why you get this trade-off, because there's always some chance that you'll be farther out on the tail, and there's some chance that you'll be even farther out on the tail, and some chance that you'll be even farther out on the tail. And as you get farther and farther and farther out on the tail, the ratio of these probabilities diverges. But this is how you get your collection of epsilon delta pairs.
Thank you, Sue.
I hope that was helpful, and I'm happy to try to do better one-on-one later.